So in this part of the video, we will continue the engineering mathematics course with the topic of power series solutions for differential equations. All right, so at the end of this video parts, you should be able to find the solutions to ordinary differential equation, ODE, with non-constant coefficients using power series. So previously, you have been able to solve for ODE with constant coefficients using the method of undetermined coefficient, variation of parameters, or for simpler ones, you can separate the variables and so on. But in this case, we want to work on the non-constant coefficients for ODE using power series method. So what is the power series method? So this power series method is the standard basic method for solving linear differential equation with variable coefficients. So anything with variable coefficients, the standard method is to use power series method. So it will give the solution, i.e. the function of y as a function of x in the form of power series. So what is a power series? Power series can be is an infinite series of the form this equation. So this is equation 1. So we will use this equation a lot throughout this video or in this topic. So the standard power series in the infinite series form is this summation from n equals to 0 to infinity of a sub n multiplies with the x minus x naught to the power of n. So if you expand this the power series starting from n equals to 0. So when you substitute n equals to 0 in this, then you will get the term a naught times x minus x naught to the power of 0 plus a1 times x minus x naught to the power of 1 plus a2 times x minus x naught to the power of 2, and so on and so on. And until n equals to infinity, not equals to infinity, until infinity. So you can simplify this term because this whole term here is equal to 1 because everything to the power of 0 equal to 1. So you will just have a naught and then time plus a1 times x minus x naught because it's to the power of 1. So it's just that plus a2 and so on and so on. And look at the power. So this is the expansion of the infinite series of this series formula. So what are the terms inside the power series? So a naught, a1, a2, a3, a4, and so on are real constants called the coefficients of the series. X naught is a constant also. So x naught is called the center of the series, and the variable is x. Okay, so x is a variable. So in particular, if x naught is equal to 0, then the power series is reduced to just this because you don't have the x minus x naught. And initially, you have this x minus x naught to the power of n. But if your x naught is equal to 0, so you can just eliminate this term and just have x to the power of n here. And when you expand the series, you will get a naught plus a1x plus a2x squared plus a3x cubed, and so on until infinity. Right, so these are some familiar examples of power series. We will have a look at how to derive some of these series later in this video. So just to have a look, just to give you some familiar examples. So this term expression here, you can express it in power series. And when you expand it, you will get this. And for e to the x, the power series form of this function is this, and when you expand, you get this, and so on for cos x, sin x, and for ln of anything, something inside here. But in this case, it's ln 1 plus x, so you get something like this. Okay. So let's go through some basic concepts of power series before we indulge ourselves in using power series to find the solutions to ODE. So from equation 1, i.e. the original power series expression, so when you expand, you get this. So let's look at the nth partial sum of this power series, i.e. When n equals to some number of n, i.e. we stop the power series to n equals to n instead of going on and on until infinity. So we take the series s sub n, meaning we stop until the nth partial sum, okay? So we stop the series at an and x minus x naught to the power of n. So when we stop that series at n equals to n, the remaining expression, i.e. starting from n equals to n plus 1, is called Rn, okay, R sub n. So R sub n starts from n equals to n plus 1 until n approaches infinity. So this is called the remainder of the series 1 after the term an times x minus x naught to the power of n, i.e. you take the partial sum until n equals to n, and whatever remains from that series starting from n plus 1, you call it a remainder. So R of n is called the remainder of this expression here, and starting from n plus 1 and so on and so on. Okay, so let's have an example. Let's do an example here. Given the geometric series here, find what is S1 and what is R1. Okay, so let's do that in the whiteboard. Okay, go to the whiteboard. So for this example, you have the geometric series 1 plus x squared plus and so on until x to the power n and so on, right? So for S1, i.e. when you just stop at n equals to 1, then you get S1 equals to 1 plus x, because this is what you get from n equals to 0, this is n equals to 1, n equals to 2, and so on and so on. So S1, the partial sum when n equals to 1 is equal to 1 plus x. Thus, the remainder of 1, R1, is what remains from the series, i.e. starting from this part of the series until n approaches infinity. So R1 is the remainder, x2 plus x cubed plus x to the power of 4 and so on until n approaches infinity. And looking at the same series here, so what would be S2 then? So S2, i.e. when n equals to 2, you take the partial sum of the series at n equals to 2. So you will have 1 plus x2. So you stop there. And the remainder of 2, R2, is whatever term starting from n equals to 2 plus 1, i.e. n equals to 3. So start from x to the power of 3, x to the power of 4, x to the power of 5, and so on until n approaches infinity. Okay, so that's the first example. Easiest example first. So go back to the slides and we look at some basic concepts of power series. We continue, okay? So still taking the equation 1 as an example of our power series here. So if we take the limit of the series as n at x1, and as if the limit of Sn when x equals to x1, as n approaches infinity, then the value equals to x1, i.e. now the series is convergent at x equals to x1, then the series is said to be convergent at x equals to x1. Okay, so when the series converges at x equals to x1, you said that the series is convergent at x equals to x1. So this number as x1 is called the value or sum of equation 1 at x1. Okay, so initially the equation 1 is n from 0 to infinity, an x minus x naught to the power of n. So when you replace this x with x1, and then as n approaches infinity, then you get the Sn of x1, this value. So it converges to a certain value. Then this number and S of x1 is called the value or sum of the equation 1 at x1, x equals to x1. Okay, but however, if the sequence is divergent at x equals to x1, then the series is said to be divergent, i.e. if the sequence diverges, okay, if the sequence diverges, at x equals to x1, i.e. there's no defined number. As you see, when n approaches infinity, there's no limit. Thus, the series is said to be divergent at x equals to x1. When you replace this x in the original equation with x1 and it diverges, then it is said to be divergent. Okay. So convergence versus divergence, how do we determine and define if the series is convergent or divergent? So the series 1 converges at x equals to x naught when all its terms except for the first a naught are 0. In unusual cases, this may be the only x for which equation 1 converges. So sometimes there is some series here. So this is your equation 1 again. Sometimes x naught, only when you replace x with x naught, the series will converge. So this is very unusual, and then meaning all of its term will become 0 except for the first term a naught. But in some other cases, the series may converge at certain interval of x values and may diverge at other interval of x values. So so let's say you still have this series 1. Oops. So this is your series 1. So the series 1, let's say it converges for all x, for all value of x, such that when x minus x naught is less than r, and it diverges for all other x, such that when x minus x naught is greater than r, the modulus of them. So here x naught is the midpoint, and r is now the radius of convergence. So how to determine the radius of convergence? We can use either this expression, this formula, or this formula here. So next thing we will try to find out if the series is convergent or divergent using this test. So the convergence interval may sometimes be infinite because sometimes the series 1 converges for all value of x. Then we say that the radius of convergence is infinite, okay, infinity. There is no certain values or limits when the series will converge. It just converges for all x, all values of x. But now how to determine if the power series will exist for all values of x? Because we know that not every series will exist for all value of x. So it makes sense to us if the power series will exist for all values of x. So this one we can find out by looking at the convergence of the power series. So we say that the power series converges for x equals to c if the series, if this series is a finite number. So if you put x equals to c inside, and when it approaches infinity, when n approaches infinity, and you see that it converges, it has a limit, then you say that the power series converges for x equals to c. Okay, so this power series will always converge also when x equals to x naught. So in this case, the power series will become just the value of a naught, because all the other terms inside the series, when you expand, it will become 0 because x naught minus x naught is 0, but except for the first term, because anything to the power of 0 is 1, so you will be left with just a naught. So looking at this fact here, so given a power series equation 1, there will exist a number. This number is the row. Okay, so this row here, this number ranges from 0 to infinity, so that the power series will converge for x minus x naught less than rho, and diverge for x minus x naught greater than rho. This number is called the radius of convergence. So rho is actually of the equivalent, is equivalent to r, the radius of convergence. You know, this r that we see before, this one. Okay, so r and rho are can be used interchangeably. So some books use r, some books use rho, some reference or videos also use r and rho. So just know that they are of the same meaning, i.e. referring to the radius of convergence. So let's do a test for convergence for a power series. So there are some methods to to see whether the power series converges or diverges, that is convergent or divergent. So first test is to see if the limit of the power series, so U sub n is actually the power series as n approaches infinity. So if the limit of the series as n approaches infinity is equal to 0, then we can say that the series may be convergent. But if the limit of the series as n approaches infinity is not equal to 0, then the series is certainly divergent. You see that there is no certainty here. It says that, let's say the limit equals to 0, then the series may be convergent. It doesn't say that certainly divergent. It only say that, okay, there's a good chance that the series here may be convergent if your limit is equal to 0. However, if the limit is not equal to 0, then you can be certain that the series is certainly divergent. Another test is to use the comparison test, similar to what we have learned earlier in the early topics of integration, where we want to use comparison test to see whether the function is convergent or divergent. So we can use a standard series where you can see, what is the value of the power here, the index here, to see if it is divergent or convergent. So you can look at these numbers, the P here. So for P greater than 1, the series will certainly converges because, when 1 divided by something to the raised to the power of greater than 1, so the denominator in all of these terms will be larger than 1. So when you add them, it will converge to a certain value. Okay, so it says that, it means that the series will converge, definitely will converge if the index at the denominator here is greater than 0. However, if the index of the denominator is less than 1, the series diverges, because when you divide 1 with something indexed to the something that is less than 1 to the power of less than 1, then the denominator here will become smaller and smaller and smaller. Thus 1 over something smaller will become something bigger, and it will diverge. It will not converge to a certain finite value. Another straightforward test for convergence for power series is this ratio test, the Lambert's ratio test for positive terms. So you can get the value of rho here by finding the limit as n approaches infinity of the series at n plus 1 divided by the series at n. So look at the value of rho. So if rho is less than 1, you say that the series converges. If rho is greater than 1, the series diverges. But if you get rho equals to 1, you don't get to conclude anything about the divergence or convergence of the series. So you have to use another test. You have to use other method to determine the convergence of the series. Okay, and another method is number 4 for general series. Okay, so if the summation of the series converges, then the series is absolutely convergent. However, if the series of the modulus of the series, if the summation of the modulus of the series diverges, but the summation of the series without the modulus converges, then this series is conditionally convergent. So there may be a radius of convergence that you need to find out to see where it converges and where it diverges. So I put here a QR code to a YouTube video for you to look at further on the use of this ratio test to test for the convergence of power series. But we will do the example anyway in the next slide. So just scan this QR code here, okay, for you to follow through the examples. Meanwhile, we will still do examples. Just bear with me when I switch from slideshow to exiting the slideshow. My computer always do this. Okay, so let's go through example 1. Okay, so now we want to find the radius of convergence for the following series. So let's look at number 1, example 1 here. So this one, we do it in whiteboard. Okay. All right, so we're going to use the Lambert's ratio test to test for the convergence of this power series. Okay, so what does the Lambert ratio test say? That we need to find the regions of convergence, the rho, by looking at the limit as n approaches infinity, and then the modulus of un plus 1 over un. Okay, so you write down the un plus 1 over un. Okay, and then plug in the power series. So for n plus 1, it's k plus 1. Okay, I think I'm going to need to use the PowerPoint blank slide because it's not working on me here. So just bear with me here. Okay. Right, so okay, just continue. Sorry for the technical error, technical problem. So go back to the ratio test. As n approaches infinity, un plus 1 over un. Okay. Okay, now un plus 1 over u of n, okay, equal to, so now you can just replace the n with the k, okay, because the series you're given is k over 2 to the power of k. So now instead of n, we use k, uk plus 1 over uk. So k plus 1 over 2k plus 1. This is your uk plus 1 over uk. So just the original series. Okay, then just be careful because you have ratio of fractions. So just k plus 1 times 2k over k. Okay, then you can further simplify this. K plus 1 over k times 2 to the power of k over 2 to the power k times 2. So you can eliminate these 2k term here. So you will just end up with k plus 1 over k times 2. Then you use the ratio, you find the row, so n of or k now, as k approaches infinity of the k plus 1 over 2k. So then you can take out the 1 over 2 because it's a constant. So you can just focus on the terms with k here. Okay, so as you can see here, so k plus 1 over k, so something plus 1 over something. So as the something approaches infinity, then the plus 1 will not be as significant. So this value here will just be equal to 1, right? So this will just be equal to 1. So your rho is thus equal to 1 over 2. So since the rho is equal to 1 over 2 and that is less than 1, then the series is said to be convergent. The series converges, or you can say the series, the given series is convergent. So the given series, the original one is from from k equals to 1 until k approaches infinity. So this series is convergent. Yeah. Okay, so let's do another example. So the second example is this. So you have this. So let's use the same ratio test here. Okay, so Yep, just follow through the ratio test. So here now your u k plus 1 over u of k becomes -1 k plus 1 times x minus 3 k plus 1 over 3k plus 1 times k plus 1 plus 1. Well, you could have written k plus 2, but then I just want to make it a point that it is that plus 1. Okay, we can simplify things later. So this whole thing here divided by -1 times k, m to the power of k, x minus 3 to the power of k and 3k times k plus 1. Right, so then be careful when, just simplifying the terms with double denominator. Okay, so, you can simplify things now already. So x minus 3 to the power of k times x minus 3 over 3k plus 1 k plus, I think you can simplify it already, k plus 2 here, because you can't be eliminating that anyway. So just put it k plus 2, and then here becomes 3k times k plus 1, and then -1 times the power of k x. Okay, so here the 3k plus 1 you can also further simplify to 3k times 3. Okay, now you can see there are terms that you can eliminate. I'm going to change the color. Okay, so you can eliminate this one, and you can eliminate this one. You can also eliminate this 3k. So you, you have, I think that's all right that you can eliminate. So so then you continue with those eliminated things. So -1 times x minus 3 times k plus 1 divided by 3 times k plus 2. Okay, so this is your uk plus 1 over uk. Now we're not done yet. So the next thing we need to do is to find the radius of convergence. So the radius of convergence is limit as k approaches infinity of -1 x minus 3 k plus 1 divided by 3 times k plus 2. Oops. Oh. Okay, now well, looking at this term here, so the inside of the modulus have the term k, and we don't want anything to do with the x, other than the k. So we take out anything that is not k outside. So we take out the x minus 3 and 3 modulus, and then we take the limit only as k approaches infinity. -1 times k plus 1 over 3 times k plus 2. Okay, right. So here you need to find out what happens when k approaches infinity. Okay, inside here. So what happens as k approaches infinity? So you can try to figure it out on your own. So this is the whole thing here is 1. As k approaches infinity, the inside will be approaching -1, but we just want the modulus, so we just take 1. So rho equals to the modulus of x minus 3 over 3 times 1. Okay, so then we want to find out the radius of convergence. So there's this conditional convergence. So we know that the series converges when rho is less than 1. So when rho is less than 1, the series converges. So we want to find out what would be the convergence radius. So x minus 3 over 3, because the modulus of 3 is just 3, right? So less than 1. So then you get x minus 3 less than 3. So when you take out the modulus, you change the sign, then you have x greater than 6. No, sorry. Okay, so you have x smaller than 6, and also you know that the series will diverge when rho is greater than 1. So you also do when okay, minus of x minus 3 is less than 3. Okay, so you see that the radius of convergence is between 0 and 6. So x must lie between 0 and 6. So thus the radius of convergence is 3. Radius of convergence is thus 3 because you know the series converges from x equals to 0 until x equals to 6. So the midpoint is the 3. So this is the radius of convergence, you know, just the center of the whole thing. Okay, so let's take a break before we proceed to the next video. So in the next video, we will look at the operations of power series. Okay.